Hello, and this is my presentation on solving differential equations with digital signals processing. Before I get started, I would like to say that a vast majority of our understanding of physics is linked by differential equations, figuring how things can change in time. Starting with Newtonian physics and moving all the way through quantum mechanics, differential equations is an integral field for the study of the motion and interaction in bodies, of chemistry, and of electronics and electrical engineering, among many other areas. Now, many differential equations can be solved. The linear cases, the Bernoulli equations, many first-order cases, but there are many such equations whose solution cannot be expressed in the closed form. Consequently, numerical methods must be resorted to, and this is where my presentation is researching. We can approximate an integral by using this sum here of discrete samples of a function x. There are two ways to do it. You can sum them all at once, or you can take the previous sum and add the next term, where the previous sum is yn minus 1 and the next term would be tau of x at this next sample. This allows us to write code in MATLAB which can solve ordinary differential equations by direct numerical integration. The work here shows the equation y prime equals dy dt equals y squared minus 30 run from 0 to 2 in the time domain. When this is done, as tau approaches 0, the solution converges to a limit, the limit being shown by the black curve and tau at a larger value being shown by the cyan curve here. Of course, you might wonder why I mention this work, since it is taught in Cal 1 and Cal 2. However, notice the yn equals yn times tau times that, and how that is added to the solution matrix here. I will explain how this works momentarily. No, it's a plus, so yn equals yn plus tau times the next sample. That equation just mentioned is a difference equation, not unlike the ones we covered in this course. So taking into account a different example, this first order linear case, so I can compare the actual solution to the computer solution, you can convert this by direct integration, numerical integration, into a difference equation shown here, where this is the previous integral, the term you're adding, and the initial conditions respectively. And then the z transform can be taken for this difference equation, and the solution can be found in the z domain as shown by the fourth line here. I chose a simple example, so the inverse z transform y of n, the fifth line, can be found by hand. Now, of course, converting back to the continuous time domain or its approximation, the actual solution is a limit as tau goes to 0. However, it is possible to convert between ordinary differential equations to difference equations, solve these using the z transform, and then obtain the solution trajectories. When the hand inverse z transform was taken, plots were generated. As can be seen, the limit process exists. So for example, a tau of 2 or of 1/2 renders the purple curve, tau of 10 renders the red curve, and higher levels of tau converge onto the black curve, which is the solution to the previous equation here, the first line, where k equals 1, and the initial condition is 2 at time 0. And the black curve is the solution found by hand. So the method has merit as shown here. In addition, a situation arises where it may be impossible to find the inverse z transform by hand. What is one to do when this situation may occur? The answer is pretty clear. The function iz trans f, where f is the z-domain solution, can be used via MATLAB to find an approximation to the inverse z transform, and from there a loop and a plot statement, as shown here, can render the same trajectories as were seen on this page. So even if it was the case that the inverse z transform could not be found by hand, numerical methods as introduced in this course can be resorted to, which will solve nonetheless the difference equation, and therefore the solutions to the differential equation can be interpolated. So my results of this work show that DSP can be used to expedite differential equation solutions. Two methods are shown on how this can be done, and both render valuable solution trajectories. In both, MATLAB is instrumental, although Python or Java, etc. could be used if need be. And material from this course is therefore linked to a real-world problem and practical application. I cited these works, among others, during this research. Thank you for listening.